Welcome everyone to another OCP Tap call. This is call number 163. So it's a very special day today because this is the 6th anniversary for OCP Tap, and then is the first time in the 6 years that the biweekly call is also back on July 15th. So basically 2,192 days since July 15th, and it's today. So with no further ado, it's like we'll introduce our speaker. So I'm pleased to introduce our speaker today, Liang-Min Wang. Liang-Min has many years of experience in microprocessor-based system performance optimization, working across platforms including SPARC, Alpha, and x86. More than a decade ago, he began focusing on network device virtualization for SDN, bringing deep expertise at intersect of system performance, networking, virtualization, and timing. Liang-Min retired from Intel in 2024 after 24 years career and joined Marvell in 2025. During his brief retirement, he focused on integrating PTP for SDN technology with the Linux operating system. And in his current role at Marvell, he is developing test strategies for assessing PTP accuracy across both the PCIe and MAC layers. Today, Liang-Min will present PTP for SDN, a software cross-timestamping technology for PTP provisioning in virtualized environment. And his talk will cover how this approach supports applications running in both container and virtual machines. And he will share test results showing timing accuracy with standard deviation under 100 nanoseconds, even under network workload conditions. With that, I'd like to welcome Liang-Min and hand it over to him. Liang-Min, thank you for joining us. The floor is yours.
Thank you. By the way, let me do the voice checking. Can you guys hear me clear?
Yes.
Okay, thank you. Ahmad, thank you for your kind introduction and the invitation to this forum.
You're welcome.
The material that I will present today, as I show on the screen, right, it's mostly based on the paper I co-authored with my colleagues, Tim Miskell and John Morgan, while I was with Intel. And
Yes.
The paper was originally accepted as an 8-page full paper, then reduced to 6-page because the presentation was moved to a different menu. So you may find out some additional material which was not covered by the norms paper, but actually we present the content in the conference last year. In short, because I'm no longer with Intel, I would like to make a disclaimer. Today's talk doesn't reflect Intel's position in PTP cross-timestamping technology. The data shown in today's presentation were correct with Intel processor and network device spent 2+ years between 2022 and 2024. So the performance data doesn't reflect the progress of Intel process technology as of today. And I also joined the Marvell in 2025, but I did not continue working on developing PTP for SDN when I'm with Marvell. So what I will present today also doesn't reflect any product of Marvell. Okay. With that, let me proceed to today's presentation.
Perfect. Noted.
Okay, today the agenda will include first the problem statement. In this section, I will explain why we came to develop the PTP for SDN and what is the problem that we intend to solve. Second, I will discuss state of the software-based PTP clock synchronization. In this section, I will present some performance number, which I obtained from literature research and from some open source between year 2022 and 2023. So it may not reflect what is available now. And then I would go to the serial design and timing accuracy assessment method that we deploy. I will give a high-level description of the main technology that we developed for PTP for SDN. And then I will follow to go into detail about some key innovation that we developed for this technology. Then I would discuss the timing accuracy assessment with the two different approach. Then the next part, the VRAM use case, is the one that was omitted from the final paper, but I did present during the conference. So I'm going to present here. Then I will conclude today's presentation with a Q&A session. Okay, the problem statement. So in 2022, my colleagues in Intel and I, we received a request from a public cloud vendor to support provisioning PTP cloud service inside of VM. Up to that time, all the VM deployment was through container, as far as we know at that time. Our understanding, the reason behind this request is that the provision service inside of VRAM inside of VRAM represent a better isolation in internal security. The virtual machine VM is implemented through this address isolation, right? Each VM is in different process and different address mapping. So it provides a better fault tolerance compared to name-based isolation, which is the key technology behind container. So we understand our customer who support public cloud, they support multi-tenant. So in order to achieve a better security, they would prefer provide the service inside VRAM. So we did some study, and we find out that we did some study. So we look at, in this case, we look at two OS, Linux and VMware. For the Linux, since it's an open source, we are able to run some quantitative study. So from our study, 24-hour run of looking at the PTP clock inside of VM, we can see the jitter come out, the spike come out very frequently, and the spike can reach more than a microsecond, sometimes a couple of microseconds. And then because it's open source, so we are able to instrument the code, and we realize the way that the PTP was provisioned to a VM is through this hypercore. And the hypercore is sensitive to the system jitter when workload heavy, right? When we did this study, we didn't do any special arrangement such as put the higher priority for the service running the PTP KVM. So with that, we can see the jitter. And for the VMware, we at the time we did not have the tool, and because it's a proprietary, so we don't have the source code to investigate. So basically, we look at the literature, and we came to realize the PTP provisioning inside VM is through a trust VM, which is a high priority VM, or this is a special VM. So after that, our conclusion was that both technologies are not adequate for our cloud vendor customers. So we decided that we need to come up with a new solution. And while we developed PTP for SDN, we came to know there was a separate effort inside Intel developing this hardware close time stamping. And for some of you might be familiar because this work was presented in this forum back in August 2023 by Dr. Standen. Even though look at the data provided by the hardware time stamping, the timing accuracy and the system jitter performance both are very promising. But unfortunately, it was not available. This feature was not available at the NIC that our customer used to deploy their cloud service. So that's the first challenge. The second challenge is that the hardware cross timing only available to the PF device. PF stands for physical function, which means if you want to use this feature, you have to pass the PF function into a VM, and which would greatly reduce the utilization, because once you pass the VM, the host lost control of the device and the service only available to one VM. And we also find out, as I discussed above, right? The provision is OS dependent. So, which is even though our customer only request the service inside the Linux, and we realized, we want to come up a solution which is not so sensitive to the target operating system. So, based on the challenge I described here, that we decide to find an alternative to support provisioning PTP cloud services inside a VM. Okay, so before we dive into, we first want to understand the state of the art, right? So we do some literature research, and we look at the open source to see what's the state of the software-based clock synchronization accuracy. In this table, the first two row data from DPDK, as I put on the note here. This is the special DPDK version designed for VMware. So in this two column is based on the EA10 device, and the virtual function use this proprietary communication between the VF and PF, and to acquire the PTP timestamp from the PF device. And you can see on the first row, right, that the performance is very poor. It's about almost a millisecond, right? This is because the IPC, even though it's done by the hardware doorbell, but it's still subject to the system jitter. And the second row is I modified the original code, try to come up this round trip delay estimation. But even with this correction, it's still not a very promising. It's still in 150 microsecond. So I did some literature survey, as it pointed on the bottom of the slide here, and that's the column, row column 2 to 5, and we see the information I researched. The best I can come up is around 5 microseconds. So we decide to come up a timestamp conversion equation, which I call clock forwarding. And initially, I was used static clock ratio. The clock ratio is the frequency between CPU clock and the PTP clock. And when I did the initial implementation, the best I can achieve is around 5 microseconds, which is still far from the requirement. So I look at the, I forget, hundreds, thousands of data, and realize that there's a pattern. And if I change the equation, allow me to change this clock ratio runtime, and the performance can be improvement. So I change the equation. Eventually, I can reach this sub-microsecond accuracy, and I will discuss the full technology from the below slides. Okay, so serial operation, right? So behind the PTP SDN, the key core technology is the timestamp conversion equation. that correlated to CPU timestamp and PTB timestamp. So meaning that we can use the CPU to derive the PTP timestamp count. In our early publication, we used the word forwarding because the two timestamp, that one carry the other one. So that's why we choose the forwarding. And I did not use cross timestamping because at that time we are not aware of there's a separate effort. And also I keep this clock forwarding in this slide because I want to emphasize that the whole design is ground up. It's not try to solve subtilation of the hardware cross timestamping. Because we studied the literature, we realized that many of the software approach always try to come up with a software solution to fit the hardware scope. For example, the jittering is a key contribution from this work because our define of shift purely from the software perspective, not from the hardware such as noise. Okay. So I will discuss. I will discuss in the subsequent slide about this system jitter removal algorithm that we came up. Then the other technology we came up is this host and VM timestamp synchronization because for the secure reason, all the virtual machine will try to come up a random number, so it would separate even we are modeling the VM the same process as the host system, right? It would always have a lag on the CPU timestamp, and the lag is not a constant; it's random generated by the VM. And in order for us to provision the PTP from host to VM, we need to find out this value, and this value is not available from any kernel source. So we come up with our round-trip delay estimation, which is very similar to the AO2.1 standard. Okay, we use this round trip to estimate the CPU timestamp count offset only at the VM bring up one time. Okay, then you can save this value for the future calculation. And finally, I'm going to talk about a integrated framework. That's the PTP for SDN, right? So we unify a framework, allow a provisioning system sitting on the host OS, and be able to provide the consistent PTP timestamp count to service running on the host at the container or service run inside a VM. And then I also will present the test methodology and the result that we came up. So there are two different test methodology we use. One is the CPU-based one PPS method, okay, and the other one is the traditional PPS and the TGBIO based PPS. The TGBIO T means time aware. So this is a variation of the GPIO, allow you to include time into the programming parameter. Okay. So let's first look at the gamma equation used by this PTP and for SDN. The two red line is the software implementation of the timestamp capture. Okay. And on right hand side, this is the fine grain describe the difference between this implementation. So, you know, when CPU issue the read timestamp count instruction. So the first line here is simple, just one assembly code, right? Because it's by x86. I have to say that we only test on the x86. We have not tested our implementation on ARM yet. I realized in the ARM there's no read timestamp instruction is a co-processing instruction, but we have not done test yet. And the second instruction statement here is to read the timestamp count, even though the timestamp count register is 64-bit. In most of Linux device right now, upstream Linux driver, they use two 32-bit read. Okay, so here our focus is the first read and the CPU timestamp count read. Okay. So from this diagram, simply you can find out, right? Because this is a software implementation, so there's a gap between the time lag between the CPU timestamp count and the PPT timestamp count. And the time can be brief captured by these three timing parameters. So we call the sum of this number as the C gap. And through the frequency ratio, clock frequency ratio, we can convert C gap to B gap, right? So this is a constant. We don't have the parameter from any of the menu we can find, but we can do a prior test. So before we run the timestamp, we use this TGBI. We are able to estimate this value, and this value in our ongoing, in our 3 years testing, it seems is very reliable for from the same CPU. If you look at this diagram, right, this C gap is a summation of T1, T2, and T3, and those three parameters are all related to the CPU. So we did it design because our base is that if we do one calibration, then no matter what we change the network device, this parameter can be applied. And from our 3-year investigation and hundreds of thousands of the tests, we see this number is very reliable. Okay. So let me explain a little bit about this governing timestamp conversion equation here. So I explain what GP gap is. And the offset is the one I described between the host and VM, the CPU offset. So if this is running on the container on the host, the offset is 0. But for any VM, right, it would when VM putting up, there's a synchronization process I'm going to discuss later that will find out the offset value. This value is saved in the VM. Okay, the PF and TSC red is the last known good pair of timestamp when every time you run these two statements, right? Okay, so you will save a CPU timestamp count here, and you will save a PTP timestamp count here. Okay, so when in the application, if there is when you try to query the PTP, instead of go to the system call or go to this get time of date, which is a Linux special function, I call a user space available system call, right? Without overhead, no overhead to get the PTP. Even you need to go through that function to get, but with this equation, you can derive the PTP timestamp count without that system call. Okay, so and R here is the clock ratio between the CPU frequency and the PPU frequency. So with this equation, you can derive a estimate PTP timestamp count. Okay. So here is the clock filtering. Okay. So on the right side, I have the algorithm description in the paper, and left hand side, I use the diagram to illustrate the pattern we try to capture. Okay. So let me first describe the error, the definition of the error. Okay. So in the previous slide, I showed we can estimate the PTP with a given CPU timestamp count at the time at the iteration I, right? But at the same time, at the iteration, for example, here in the T1, we capture a timestamp pair, a PTP and CPU timestamp pair here. On the T2 here, right, we can capture the other timestamp pair. But also at the T2, we can use the CPU time difference to estimate what's the PTP at the P2. So the error is defined as the difference between the estimated PTP and the capture PTP. Okay, with this value, we give a tolerance. Okay, so in this equation, we have two input variables. The threshold is the tolerance, right? The tolerance between between the expected value and the range here. Okay, so the fresh period is the period between T1 and T2. How often, how frequent we do the timestamp capture. So with that, okay, we try to capture 3 patterns. And for those people familiar with the PTP popcorn spike filter, you might feel this is very similar. And here I want to clarify that when we did this, develop this algorithm, we are not aware of the NTP popcorn spike filter, and there's a major difference between this algorithm and the PTP and the popcorn spike filtering. Okay. First, this threshold we have here is based on our prior testing. To understand, in the paper we show, we run many times testing. We use the different threshold. Then we calculate the error, right? And we draw a curve. It's a concave. It's an upward concave curve. That means there's optimum. There's a optimum minimum value there. Okay. So based on this test, we derive our threshold for the algorithm. Okay. And I believe in the popcorn spike filtering, the threshold is based on moving average, moving standard deviation. Okay, so that's a very different approach. And second, our design here is not just to capture the pattern 1 spike. We also try to capture pattern 2 and pattern 3. Let me explain, right? The pattern 1, the spike is that when you see when you measure the error as I define here, when the error is outside the permissible range, means that your expected value plus the threshold, right? Then it's considered a not long good. So you keep this value and you can continue move on. So you don't update the last known value, so you continue move on for the next iteration. Even the next iteration, you calculate the value is in the range, expected range, right? Because this is equal, this you can base on, hey, you pass two time period, right? And you apply to the equation, you can calculate what's the expected value. And if the value is in between the range, right? Then you will consider T2 just a simple spike, then you can just ignore, right? And then at T3, you update, then you update your last known value, okay? So if in the T3, you calculate a value which is still outside based on the first reference value, then the second jitter calculator comes in, which instead of use the T1, they will use T2 here, okay? And you calculate this value. If the value calculated from T3 is still outside the range, permissible range, for T2, then this is considered pattern 2. That means consider you have a new system overhead environment that you need to adjust the clock ratio to adapt to a new new relationship between the PTP clock and CPU clock. Okay, so that's the pattern 2 here. In pattern 3 is that once you use P2, then P3 will fall within the permissible range. Then you say, okay, now this is a new environment, but you don't need to change the clock frequency. So you can keep using the same clock ratio to calculate to the PTP TS estimation. So this algorithm allow us to, based on the last known good timing timestamp count pair, to decide if now the system is enter a environment. Now you need to adjust the clock ratio, because we are talking about nanosecond accuracy here, even though the clock frequency doesn't change, but because the system jitter change the relation between the PTP timestamp count and CPU timestamp count. As we know, requires all impact by like a thermal, or and in this case, because we use a CPU, you also you would change because the system workload. So next here is the slide illustrate how we use this server client model to ensure when there's a multiple VM, right? How do you exchange? How do you find out the CPU offset between two OS environment? One is on the host, the other one on the guest, right? So we use client server to guarantee only one VM can do this timing exchange with host. And in our case, because we run multiple timestamp exchange, so we can come up a average value, statistical average value to find out a better accuracy. So we need to guarantee only one client is exchange timestamp count with the host. And we try to avoid any system performance degradation, particular cache performance. So we create a proprietary 64-byte timing format and L2 format, right? So this is exchange between the a request from a VM and the host target service. So with that, we can calculate a accurate offset between the CPU host CPU timestamp count and the guest timestamp count. Okay, so after those core technology, let me talk about the framework, right? The way, how we, based on the aforementioned technology, we come up a software-based PTP time clock provisioning for service running inside either a container or inside a VM. So on the left side column, left bottom side column here, this is the service running in the user space, okay? And we still rely on the physical function running on the kernel space to provide the timestamp. But in contrast to the original DPDK implementation for the VMware, because we are carry to timestamp, so our accuracy is not impacted because the system workload on the IPC latency, right? Because the two times, as long as the two times is close adjacent each other, it can provide a correction as we display on this equation here. Okay. So as I described, and you know, the host would send out broadcast it's a multicast address allow VM to request for this CPU timestamp synchronization. Once it finished, it set the data on locally. Okay, so this is a continuous running, you know, with a refresh period. On each period, right, it was sent out from the host it sends out three information, which is the PREP and the clock the PTP and the CPU clock ratio R and the CPU rep through a multicast packet. So any service that would like to get this model can subscribe the multicast. Okay. And for VM, since this is calculated during the bring up time, okay, and the P gap during this for the VM, it get this value when it was trying to establish the CPU timestamp counts in violation. The host can pass this information, and for container we can just pass it as a container parameter. Okay. So every time there's a application need to get time of day, instead of calling time of day, they call in this to TPT API. Basically, use this equation, because every time you call, you will have a CPU time, right? You can get CPU time from the instruction. Then you can use that and apply this equation to find an estimate PTP time. Okay, and as long as this is accurate and there's no IOX, no system call is needed. So let's move to the next slide to see what kind of performance that PTP for SDN can achieve. So let's talk about first the setup. Okay. So this is TGP-IO based 1PPS measurement for those of you who attend Dr. Stanton's presentation 3 years ago, you should feel this familiar, because this is the setup we use from his team. Okay, so let me explain a little bit. So just like a traditional PPS, 1PPS measurement, this is the EA10 card, right? So EA10 support PPS output, so we connect this from to the scope. And usually this PPS is found on our device, but in this case, because we are access the software base, right? The timestamp from the host, from the CPU side. So we have a TPIO trigger 1PPS signal here. Okay. So the scope is set up to use one to trigger and display the offset between the two. So what is captured is the trip between the software the software timestamp achieve PTP clock accuracy compared to the gold standard, right? The one come from the network device itself. Okay. So in this case, we run the PTP SDN. Okay, and based on the timestamp, we calculate timestamp when it's close to the second, the next second. The TGBL allow us to program without suffering the latency delay, because they have a time aware, meaning I can schedule this signal to trigger X number of time units in the future. So for example, if I know the system delay is 1 millisecond, as long as I calculate trigger the schedule time 1 millisecond ahead, right? Then the time generated here, the port generator, we faithfully follow the request instead of, hey, I have to account the hardware delay. So this is the whole advantage of this time-aware GPIO, and we use this one to evaluate the software PTP SON accuracy. The other approach we come up is use the CPU core polling-based 1PPS. So as most of you are familiar, the DPDK, the data plane, to run the data plane, there are two requirements, right? The PMT driver need to run in the code, in the CPU code that will not interfere by the system task. The way to implement that is to put the CPU core that assigned to run the driver in the ISO CPU list. And also to avoid asynchronous interference such as the interrupt, the user can use this IRQ affinity, right, to avoid the CPU core that run in the PMD driver being interfered by system interrupt. Okay, because by default, system usually run this IRQ balance, right? They would assign, all the CPU core even to all the IRQ requests. With these two approach, to set up that we can guarantee, the application can own CPU 100%. With that, we can run this, just like hardware we control. So we can use time to simulate this 1 PPS, right? Almost every second, we can get the timestamp from both device. Okay, in this case, right, we use one as go, which is we run PPD SDN without any traffic. Okay, and the second is that we run PTP and SDN with heavy traffic, and also change some of our algorithm. We try to assess the impact of the accuracy. Okay, so and because we have this governing equation, even though when you acquire timestamp count pair from two different applications, we'll have slight time difference, right? But we can compensate it by use the governing equation to find the delta. So we use this approach also to assess the accuracy that is achieved by the PDP for SDN. Okay, now let's look at result. On the left-hand side, this is based on the hardware, the TCVIO based 1 PPS measurement. In this case, because we cannot get the data, even though it's saved on the scope, but we don't have the tool to access those data. So what you see here is the histogram captured by the screen. So this is data from, each data is from a 24-hour run. Okay, so in the top one is the one that we didn't apply traffic when we do the PTP SDN. And in the middle one is we apply about half bandwidth because the card we run is a 100 gig network interface card. So we generate about 50 gig traffic to see how the PTP SDN behave when system is at workload. And the last one, the bottom one, is we increase the network traffic to 95 gig. So we use packaging and running application beside in the surrounding, use the same card, right? We can create this stress on the PTP for SDN. And the right-hand side, the top one is from the 95 gig workload, right? We have 95 workload here run. And on the bottom one, we changed the pattern-based filtering, right? With simple averaging. That's what I meant, when we research literature, and when this is the common methodology used by some of the software, because they use the hardware, they come from the hardware concept. Yes, jitter is noise, and noise can be filtered out by averaging. So we change our algorithm, keep everything the same equation, but change the filtering to averaging, and we can see, besides the heavy, on the jitter, also here showing for about around 5% of the sample run outside of scope. So it's not capture is larger than the scope would display. Okay. The next slide is the slide that we use the software 1 PPS. Okay, the same thing we do here is that the top one is the one that we PTP also run with idle traffic, and the blue one is the one run with 95% of overall. We can see more variation come out outside of 100 nanosecond scope. Okay, And on the right-hand side, 17.2, we replace the pattern-based filtering with the average, and that's what we see here. So we can see some resemblance, even though it's not exactly like the hardware 1P based, but they give us a general trend match. So in some cases that we can use when we run out of the hardware or we want to get more information, we can use this software 1PPS to assess the accuracy. So next one is a use case, right? In this case, so in the 5G application, right, on the front hall, right? In this case, they put the 3 NIC card on one server, and each NIC card is a 4x25, okay? But in order to serve as a boundary clock, each NIC card need to reserve one port for a grandmaster clock. So the grandmaster clock, then they have switched, and each one could create extra port and fill in each card. So in this case, we try to see if there's a way we can use software like the Linux TS2 PHC to use one card to synchronize the other. Okay, and in general, the concern, the requirement is that, hey, if we use this one, what is considered acceptable is that accuracy had to be plus and minus 100 nanosecond. Okay, and we feel, hey, PTP4S is a good use. So we use PTPN to compare with the Linux PTP utility. Okay. And used for this inter-device PD clock simulation. So on the right-hand side, the output, right, the middle two lane is the performance exhibited by the PTP4SD, and the outside two ring is from the PHD26. And PHD26 allow an option to use one device to synchronize the other device. Okay. The red line is the standard deviation, and the blue line is the mean. And we can see as the traffic, and the X here is the traffic, right? When traffic increase, so in this case it's 25 gig, right? We only do the simulation between 5 to about 20 gig, okay? So we can see, right, the PT frequency remain very stable, even we increase the traffic here, but we can see the PH26 start to degrade and degrade increase as the traffic go to the line rate, right? And both these technologies all use the same PID controller. Okay, and the PID controller, you can look at PID controller to the software synchronization similar to the PR for the hardware, right? They all use the feedback system here. So RT is the target, the target PTP clock, right? It is the reference PTP clock, and P is the target PTP clock. The difference between the two PTP clock will be used to drive the PID controller. For those people familiar with Linux, right? Linux called PI controller because the KD here, the coefficient is 0. And I see many literature for this clock simulation feedback. The PI is enough. The proportional and the integration are necessary. Okay. So after that, the driving this through and in order for an apple-to-apple comparison, we suspect setting the KP and KI identical for both testing. So it is not going to just try to reduce the number of variable here. Okay. So the output here is driving the PID controller driving to either change the target PD clock amplitude, I mean the time step count value, or change the phase, the frequency. Okay. So we later studied the implementation of PHC26 and the PTP point. The major difference is the TQLE. So as I present earlier, right? PTP point has a governing equation. So it's very easy for us to evaluate between the two. And for the PSC to SIS, in order to do a fair comparison, because it's a software fetch the value, right? So they want to reduce the latency. So when they calculate, for example, in the P, they would do the acquire P first, then acquire R, then acquire the P again, then use the two query of P to find the average value and use that value for calculate the error. But the average is not required by the PDP for SDN because the governing equation allow us to, once the value, if you change the CPU time, you can go back to calibrate, use the governing equation. So there's no averaging happen for PDP for SDN. And through our study, we believe this is the main difference. This is why driving the difference between the PDP for SDN and the PHT2 system. Okay, let me conclude my presentation now. And so PTP for SDN improve PTP cloud provision by provide a consistent, high precision, high accuracy for network function in container and VM. As we see the framework, right? We have unified framework can provide the required parameter to any service running inside the container or inside the VM. And the way we implement this PTP SDN as I described, there's no OS dependent. We simply use the OSI standard packet, right? So there's no OS dependency. And we require no hardware timestamp. The PTP for SN require no hardware timestamp support. And last time I checked, I was able to modify the Linux kernel so instead of use the EA10 proprietary virtual channel command through the standard octal, the IOCTL interface, the PTP, I modified, add additional option, and I was able to do the same change with a couple of Ethernet driver in Linux. So we believe PTPN is device neutral. It can be applied any network device. But PTP as the one of performance is the accurate read timestamp count and low latency read timestamp count instruction, which is true for x86. And we have not evaluated other process. So this remains to be investigated. The same performance will stay with ARM and the other process. And the cost reduction as the use case I just illustrate, right? We can, before every 4 port, the customer need to reserve 1 port for the grandmaster. And in this case, if you have the 3 cards there, you need to trade off 3 ports. But if you use a software, use PTPN for synchronization, you can save 1 port on the other 2 cards. So you only need 1 grandmaster in, right? Then you can use that to synchronize the other 2, use PTP for SDN. So it's a saving, it's a cost reduction. So some potential next step. So far, we have not, as I said, I have left Intel for 2 years, so I don't know if they have further progress, but at the time I left, is just know we have not engaged any customer for on-field testing yet. And we did present to one of the customers. They suggest to engage IEEE standard, but I have not pursued. And the other potential I see here is the integration of hardware and software cross-timestamping technique, because most of the hardware cross-timestamping is based on PTM technology, right? The PTM time measurement, which is a PCIe Gen 3 standard, and many hardware support that. So I do see a potential, right? Apply the PTP and integrate with hardware to combine a framework to support a reliable PTP cloud provisioning. Okay. So this is the end of my talk today, and I'm open for Q&A. Before I start Q&A, this is my contact information and my colleague at Intel too. So I'm open for a question right now. Any question?
All right, let's have questions then. So one, I can start with one, Liang-Min. In terms of precision, like how much degradation we have when we go through all of this, and how is this like, let's say, uh, with like, like hardware timestamping versus not using hardware timestamping, and let's say all these PTM related like, improvements or technology that you use in a system.
I'm sorry, let me see if I can raise my speaker here. I have noise, I cannot hear. Let me see. Yeah. I'm sorry, I meant you mean in terms of the accuracy?
Yeah, precision.
Comparing to the hardware timestamp count?
Yeah, the precision. Like, I mean, is it like you get definitely degradation when you go like with software timestamping?
Yeah.
And can you retain some of it, like let's say when you have PTM and things like that?
Okay, I did review the presentation from Dr. Stanton 3 years ago, right? It's a hardware host timestamping. I believe their mean value is around 5, and the standard deviation is around 10 in the range. And if you look at the one we have, right? If I can go back to the slide here. Right? Even under the heavy work rate, right? It's almost 100 gig close on, because we need some traffic bandwidth to send packets. So it's you can see the mean is about 10, 10, 20 issue here. Mean is here, right? And the standard deviation is 40. Okay, so it's about 2 to 3 times worse than the hardware. But if let's look at the one, I want to point out the equation here. Let me see. I can go back to. Okay, this is good enough. In our testing, for example, the use case. Like I said, this is an estimate, right? But when you do the synchronization, this is canceled out, because when you are from the same system, this is the same. So that's why if you look at for synchronization, the industry use case here, you can see the performance is very decent here. Right? The mean value is around 10 here. No, the mean value is here, right? It's less than 5. That's plus minus 5. And the standard deviation is about 10 to 15. So it's very close to the hardware cost time. That's because in synchronization, right, the P gap was canceled out. So this is one of the variable. It depends on application. In the absolute time, yes, it's there, and the error will be contributed how we system difference. But if it's within the same system, you want to synchronize, because these two from the equation you can see that the P gap will be canceled out, so you can achieve a better accuracy here. So it depends on application.
Yeah, understood. Very nice. Yeah. Any more questions? Okay. Hearing none, then again, thank you again for today's presentation. And we'll see everyone in 2 weeks by a presentation from Thomas Hildebrand from Unify. All right?
Okay.
Bye, everyone.
Thank you.